thanks for the kind introduction, and also thanks to the conference organizers for giving me this opportunity to come to Fudan and to come to ICSME. To ICSME to share my group's recent research and also my thoughts on research. And also, as Lou mentioned, it's also kind of special that I come back to Fudan because I was a student. I became my college education here, and many years ago, and before I went to the United States to further my education. So before we start, I hope that all of us can ponder over this particular question. That is, what is the key mission of computer science? So we have a diverse audience here, and we probably have many different thoughts. So here's my take on this. That is, the mission of computer science is to help people to turn their many critical ideas into working systems as conveniently, as painlessly as possible. And also I would like to argue that software research, in particular software engineering, is at the center of this mission. And if we look at one particular metric, let's look at the more than 60 also ACM Turing Awards. And there's more than 23 or 24 of them got their Turing Awards in the area of to do with the software sciences, including software engineering, programming languages, and compilers. So if we reflect back in the many decades of our work, so there's impressive progress. So we have better languages, better compilers, better tools, environments, processes, and everything. But also it's fair to argue that things haven't really changed very much from decades ago. We still program with editor. We're still doing this like compile and debug cycle. And so, but also I think we're also at this stage of going to see some tremendous progress and breakthroughs. One thing I would like to argue that having new perspectives is everything. That is, new perspectives give us different insights and also powerful attacks to difficult problems. So on this picture here, we can look at this as a glass with half empty or glass half full. Or this one, we can either say a pretty young lady or an old man. So what I'm going to do next is to use two instances of my group research to highlight that new perspectives are very powerful. One is how to validate production compilers. The other one is how to analyze floating point code. So let's start with validating production compilers. So many of us use compilers like C and C++ compilers, GCC, LLVM, Java compilers. We probably are not clear on how complex these compilers are. So here on this figure, the data is from about 2 years ago. And if you look at for the Linux, so most of us use, it has close to 20 million lines of code. So that's a gigantic piece of software. And GCC, if you look at this, not too far, not too much less. At this point, Linux has crossed 20 million lines, and GCC is getting also very close. And LLVM is a modern compiler infrastructure, and so it has more than 4 million lines of C++. So from these numbers, it's clear that production compilers are super complex. Now the question becomes, how can we analyze these complex software systems and find important bugs? Why do we care about compiler bugs? Because even at the best testing analysis tools, you analyze your source code, they're free of bugs, but when you compile them, compilers can inject bugs into the binary that we run. So here it shows a concrete example of a compiler bug from LLVM. So probably, I don't know how many people in the audience have experienced firsthand a real compiler bug. Probably not many often, right? Usually we say, yes, a bug in my program, I should fix my own program, and it cannot be a bug from the compiler. So this one is a real compiler block. So we have a 3 small piece of C code, and we have a little. So we have a small struct with 3 fields, 3 character fields. We have a full function that takes a struct and checks the 2 fields C and E. And if they're not 1, then we abort. And then we have the main function, has a local variable, and then we initialize all the fields to be 1. And then we invoke the full function on S. So if you look at this a little closer, this program should just run normally and exit, right? And we'll compile this with clan, and compile this at -0. The executable returns normally as expected. But if compile this at -01, and then the executable gives us a core dump. So here we have real compiler bug, because the program is correct, but when we compile this with optimization on, somehow give us an error. So our goal is try to find these kind of bugs in production compilers like GCC and LLVM. So for this bug, so the developer spent quite a few months trying to understand what's going on. So at the end, they were able to diagnose and fix the bug. They said it's very, very concerning when I got to the root cause and very annoying to fix. Okay? If you're curious, you can take that link and just take a quick look. So now we have this problem that we have production compilers that are very complex, and we want to find bugs in them. So bugs that are 2 kinds. One is the kind of I show that you compile the code to produce executable, but executable does not work. The other one is that when you compile this code, the compiler just crashes. So both compiler crashes or compiler produces wrong code. Okay. And so that's a very hard problem. So how should we approach it? So the guiding vision that we have is, why there are so many programs out there already? If we have a magic way to turn an existing program into semantic equivalent ones, and the semantic equivalent ones are structurally different from the original one, then we can use the variance to stress test any compiler. So that seems to be a good idea, but when you try to execute this idea, it's not so easy. So there are a couple of challenges. One is, how do we generate different but semantic equivalent programs from the original one? So that's not easy to do. Second is, once you generate a program, how do you know the variant is semantic equivalent to the original one? Both are really, really hard questions. So we seem to get stuck. So here's the new perspective that we have. Why don't we try to relax the definition of program equivalence, not respect all possible inputs, but respect to a single chosen input I. So now the equivalence definition becomes, if we're given a variant, if we're having a variant, we want to make sure the variant behaves the same with the original program on this particular chosen input I, but on all other inputs, we do not care. And this equivalence definition is much easier to satisfy, but exploits some key interplay between 2 things. One is, when you have a program, when you have input, it's very easy to run the program on this particular input. On the other hand, the compiler doesn't know. The compiler has to compile the program to make sure it compiles the program correctly with all possible inputs. That's a much harder job. One is a dynamic, running program is very easy, but on the other hand, static compiling a program to make sure it's correct on all possible inputs, that's very hard. So that's the key idea. So with that idea, with that new perspective, we can build a testing methodology. That is, why don't we take a program P and the input I, and we just profile the run of P on this input I, and we mark every statement that is executed as green, every statement not executed as red. And then we also record the output from this program P on this input I as O. So just record this very simple piece of information. And now with that information, we can massage to the red part, the dead code region. That is, we can delete some statement from here, we can insert some statement, we can also do some deletion insertion at the same time. But all these variants satisfy this property. They're all equivalent to the original program with respect to this input I that we care about. And with this, we can find bugs. That is, we take the original program, and now we take a produced variant. If the observed output is different from the original recorded output, then we find a bug. And this is guaranteed. We don't have any false positive. Every bug we find this way is a real bug. So now let's go back to the two challenges. Generation becomes super easy, yes? And also checking becomes very easy because we just compile these two programs, compile their output. Very easy. So now let me explain to you how did we find this particular bug that I showed you earlier. So this one is the seed program that we used, the original program P. And this one, if you see that we compile at dash code 0 and dash code 1, the program works as expected, no problem. When we profile the run, we notice that all these boards here are unexecuted. So we'll be able to produce a variant that some of the boards got deleted and then trigger the bug. So usually just this program here is pretty small, but imagine that your original C program is gigantic. Usually before you report this to developers, you want to reduce this as much as you can. So here's a reduced one that we reported to the developers. So at this point you may be curious, how come this program triggered the compiler to fail? So here is some analysis of the bug. First of all, there is a compiler optimization. We don't need to know exactly what this means. It's GVN. It says, I want to load this little struct with 3 character fields. If I load that, I can have 3 character loads, right, for each one, each individual field. But I can do something smarter. I can try to turn these 3 character loads into 1 integer load, right? 3 loads become 1 load. You see 2 instructions. That seems to be a very clever move. On the other hand, there's another compiler optimization called SROA. Again, we don't need to know what that is. It says, you're doing something wrong. Because the struct only has 3 fields, now you repass over the struct n. So that means your original program must be faulty. And you see in C++, there's this convention. If a program is faulty, then the compiler can do whatever to it. In this case, the compiler says, your program is faulty, I'm going to get rid of these 3 initializations. Then, because local variables in C and C++ are not initialized, then they have random garbage and then trigger the board. So that's what has happened. But that's a mistake made the compiler. The program is correct. So that's a compiler bug. And now let's look at this C program did not trigger the bug. But the program with a few aborts deleted triggered the bug. You may wonder why. And that's not an easy, it doesn't have an easy answer. It took us a long, long time to figure out what's going on. And the reason is because we deleted a few aborts, so the function f, the body becomes a little smaller. It becomes small enough to below the threshold, the compiler decides, I want to do inlining. Inlining is a very important compiler optimization. It's because of inlining and various other things that cause the compiler to fail. And in fact, for those of you folks who are kind of like deep into programming C and C++, you can also put an attribute on this foo earlier in the C program to say, I want to inline this function. And that's also going to cause the compiler to fail. All right. So now that's LLVM bug. I want to be fair to LLVM. So let's look at the PCC bug. So this one, we have this piece of code. We have 5 global variables, A, B, C, D, E. I want to remind everyone in C and C++, all the global variables are initialized to 0, even if they don't have any explicit initializations. So in this piece of code here, and C here is 0, so that means this will not be executed. The loop will just go through a bunch of times and then quit. Yes? So this program is a valid program. It just does no job, right? Just runs this a few times. So at -0 works as expected. -03, the produce executable hangs. We have if loop. Yeah? Again, that's a compiler bug. This time it's a GCC bug, not LLVM. Right? So what's going on? So it's kind of interesting. Here we have this little expression. It's a little weird. We have this number, constant, minus b. So the compiler says b is not modified within the loop. So that means this is going to be a constant expression every time I go through the loop. Yes? So why do we waste the effort? Why don't we try to move this outside of the loop? That's called loop invariant hoisting. That's what we did. Okay. But once that is done, something terrible has happened. What terrible thing? If you look at this expression here, when b becomes -1, you add a 1 to this number, and this number is already the biggest signed integer. Then we have a signed integer overflow. The signed integer overflow is a terrible thing in C and C++. So that means the compiler will say, your program is terrible, it's bad, I can do whatever. In this case, the compiler decides to replace this whole thing with an infinite loop. That's what caused that to happen. So in the original seed, that did not trigger this bug, is because of this. There's a b++. Because b was modified, then this is not loop invariant anymore. So that's why the bug was not manifested with the original seed. All right. So this is the basic idea behind equivalence module testing. It's a very simple idea. It's really just a new perspective. How to relax the definition of program equivalence with respect to all inputs to a single input. Once you have red realization, now you have a very powerful technique. You can find a lot of bugs in production compilers. So that's what we did. We introduced this idea about 3 years ago in 2014. There is only deletion. We look at the red parts, only delete randomly. And then we refine this in 2015. We say, let's try to also add code, garbage code, into the dead code region's red parts. And then in the latest one from last year, 2016, we say, let's also try to look at the green parts. Let's see what we can do. So with this sequence of gradually sophisticated techniques, we were able to, in 3 years also, find this many bugs in GCC and LVM. And now the number already crossed the 1,400 line. And they have fixed, at that point when I recorded the number about 2 or 3 months ago, close to 800. Now it's already over 800. And so by doing that, also there's a few additional pieces of work where we try to test the link time optimizers, a modern compiler technology, which allows you to compile your code much more aggressively. The other one is, at EC 2016, was how to analyze compilers' diagnostic support. That is, we run the program, the compiler on our program, we get a lot of warnings. But some of the warnings can be confusing, can be wrong. So we were looking at finding these kind of bugs in compilers. And the other one is, the latest work from early this year is, doing testing is fun. We can find a lot of bugs, I'm very happy. But on the other hand, also you say, how many more bugs can we find? So we want to move from testing to verification. That is, we want to have some sort of practical guarantees. So in that piece of work is the first step toward doing bounding compiler verification. That is, we want to exhaustively generate all possible small test cases. If we run the compiler over all these test cases, then we have a sense of guarantee. So that's this work about. So my main takeaway here is also, we got some gracious acknowledgement from the community, from our LVM 3.9 and 4.0 release. they specifically acknowledge our contributions over the last few years. And so that's very gracious of them. And here, just quickly summarize. So EMI is a very simple idea based on new perspective. Once you have that perspective, the underlying techniques to use this new perspective is actually quite simple. And it's a general concept and very effective. And we found a lot of bugs in the last 3 or 4 years. So my main takeaway is, in research, we produce a lot of good work. Sometimes we wait for other people to come to use our technology, but usually that doesn't happen. So one thing I've learned in this line of research is you want to be the loyal users of your own tool. Apply them if you trust them. If you trust your research, apply them. Try to, report bugs or do whatever. Okay? I think that's one big lesson that I have learned over the last few years. So that's the first instance. So I'm moving on to the second instance. How to analyze floating point code. So many of us know floating point code is very, very important. And errors in floating point code can lead to costly disasters and death. But they're really hard to get right. And the reason is because floating point reasoning is very, very different from what we learned in school using real numbers. They're very different. And also in floating point code, there are many nonlinear relations that we have to deal with. Like there's square, multiplication, these kind of things. And also transcendental functions, very hard to deal with. Sine and cosine explanation. So even for this very simple piece of code on the right here, none of the existing approaches can deal with this in a very satisfactory way. Okay, that's pretty sad. So now we're stuck with this very hard problem. And most people just say floating point is so hard, that's not even worry about it. So here's our perspective. Let's look at this difficult problem from a different angle. So I'll introduce this methodology I call mathematical execution. That is, let's take a floating point program P and the property that you want to verify this program against. And this can be many things. Can be through coverage-based testing, can also be solving floating point constraints. So instead of looking at this problem directly, why don't we try to map this to a problem that maybe we have a better handle on? That is, we want to reduce this to a mathematical optimization problem. I'll call that R. And we satisfy this property. If I have input X that drives the program P to satisfy the property that you care about, then X minimizes the mathematical optimization instance. So that's kind of like a guiding principle I would like to follow. I'll illustrate this by showing you how to use it to solve floating point constraints. So here's one constraint. We have sin x equal to x, and x is greater than or equal to a very small constant. This one is solvable in floating point constraints because sin x equal to x holds when x is very small, gets to 0. Yes? But it's unsatisfiable if it's realist because sin x is equal to x in real numbers that only holds if x equal to 0. Yes? So how do we solve this? We have many, many constraints like this we want to solve. And why this is important? This is important because any sort of reasoning that you want to do with the floating point code, at the end it boils down to solve these kind of constraints. If we cannot do this, then we don't really have any technical machinery to solve problems to do with floating point code. So how to do this? So here's our idea that we want to produce this floating point program R that kind of like simulates the constraint. And the R satisfies, R has to be non-negative. And also, if R is equal to 0, that means we have found a satisfying assignment to the constraint. Okay? We want to fabricate such R. And then once we have such R, we can minimize R as if it is a mathematical function. So let x star to be a minimal point. Then the constraint is satisfiable if R at that minimal point is equal to 0. So that's the basic idea. Now the big question is, how do you fabricate this R? And how do you reduce the original constraints to this floating point program R? So here's the idea. I'll illustrate this with a few constructions. Imagine the constraints in synonym form, conjunctive normal form. If x equal to y, then we just produce this one, x minus y squared. If it's x less or equal to y, we use C and C++ ternary construct. If it's true, then it's 0, otherwise a different square. If it's a conjunction and, it's just plus. We do R1 for the first part, R2 for the second part. If it's a OR, it's multiplication. That's it. Now we can take any constraint, floating point constraint, apply these 4 rules, we can produce a floating point program. And I guarantee that floating point program that we obtain meets our 2 conditions. And now we have constructed R. The next one is how can we find the minimal points of this R? There is, we rely on local optimizations from mathematical optimization domain. And also, we use MCMC, Monte Carlo chain sampling, to avoid stuck in local minimum. So we jump over and try to find the global optimums. And we use this as black boxes. We don't need to optimize any of them. So the key here is we do not analyze the constraint, but we just run them. Run the things always easier. So how do we minimize R? Here is kind of like an illustration that suppose we start from this random point, we apply a local optimization technique, find a local optimum. And then we use MCMC to jump over to another point, and we solve again using local optimization. And this will help us quickly converge to the global minimum. And with that global minimum, we can use that to decide whether the constraint is satisfiable or not. And here we also provide some guarantee, theoretical guarantee, which is just repeated from before. There are some caveats. That is, because we're still running the program, we may be affected by floating-point inadequacies in the running, in the execution. The second thing is, because we're using local optimization and also MCMC sampling, we may not be able to find the global optimum. So, but that would be more like an empirical question to answer. That is, in practice, how well does it work? So here's an example illustration. We take the original program, original constraint, and then we produce this floating point program. And just believe me that you'll be able to find the X star like this, which makes the constraint satisfiable. And here's our implementation. So this general paradigm, we call this mathematical execution. And we build this tool called XSET, and we compare this with 2 state-of-art model solvers. One is Z3, which has some sort of support for floating point, not great, and NetSet, which has better support for floating point solving. And we use SMT competition benchmark for the floating point part. And we get 100% consistent results in the other 2 tools, but a few hundred times faster. And really kind of like move forward in having some practical floating point solving capabilities. I think it would be really great to build this kind of technology into things like Z3 and NetSet. So here's my takeaway on this part. That is, let's not be afraid of difficult problems. Let's not try to only solve easy problems. Let's try to look at difficult problems, but look at them from new perspectives. And also, let's also don't forget about the problems that are bad. Like the floating point one, right? People say it's so difficult. That's why you think about it. And also damned by research. For example, many of us probably are familiar with fault localization. Yeah, that's kind of damned by some classical papers. If you have a perspective, you can find a really good way to have practical fault localization do it. So just want to kind of like have a couple of more things to say regarding mathematical application. One is it's a very general methodology. I only showed how to solve floating point constraints, but you can use this to do many, many things. For example, you want to say, I want to find inputs to maximize the test coverage. You can do that. There's a way to do this. We have a paper that published earlier this year which shows exactly how to do it. You can find boundary values of your program. You can find runtime floating point exceptions. You can also check if you have two versions of the program, floating point implementation and infinite precision implementation. You can say whether you have any control flow path divergence, because they indicate like difficult, like important bugs. In the long run, I hope this mathematical optimization methodology can complement concrete execution, symbolic execution, and also abstract interpretation-based execution. So I think it's a very exciting new paradigm to look at. So with that, I just want to share a few additional thoughts. One is, I think in research, it's always easier for us to follow like very popular trends. Yeah? So one thing is, there's so much work on applying machine learning, deep learning, or general AI techniques to solve our problems. That's great, we should do it. On the other hand, I think we as a community also have a lot to offer to make AI technologies, deep learning techniques, much better to use. For example, we have the machinery, we have the background to understand what it means for a machine learning system to work correctly, how to formalize these things, and also how to build testing techniques, verification techniques, to find bugs in such systems, right? Because, auto driving systems are going to be with us, no matter whether we want them or not, right? And they'll be with us. So now it's our job to make sure they work correctly. So I think it's our job here, right? And also make them more usable, right? Any people who have, folks who have used the TensorFlow probably argue that it's not that easy to use, right? And we, I think, have the understanding and expertise to make them much easier to use. So the other one is, again, I said, we have made so many progress, so much progress in the last decades to make building software much easier, much more robust. But still there is a long way to go, right? One is, I think there's a few things. One is, imagine that there's this very powerful intelligent programming assistant that's part of the IDE or part of the compiler that work along with the developer, guess the developer's intention, and try to understand when the developer has difficulties or wants some additional information, try to push this information proactively to the user. And the second thing is compilers. Mostly we use compilers to compile code for machines, not for us, right? But compilers have done a lot of analysis. We should open up the compiler, give that information to the developer. We can also empower compilers with SMT solvers, all these like fancy techniques to make them more usable for developers, not for machines only. And also large capture and reuse. That is, many times when we face a problem, other people have come up with solutions already. Yeah? It's just we don't know where to find that information. So I think it would be great if we have ways to try to push along this direction, how to capture all the programming wisdom that is, and also how to give that information to the user. And also anything that is closer to our key issues, that is how to help people turn ideas into working systems as quickly and as robustly as possible. So with that, I want to thank you all for the invitation.
Very impressive. So we have plenty of time for questions.
Thank you, Sindang, for the great talk. In the first making works in compilers, how did you come up with the
Yeah, so that's a great question. So the question is, how do we, in the first part, on testing compilers, we need to use the C program. How do we come up with C program? So there are many sources for this. One is that there are so many like open source projects that you can use. And we did that for a while, but there's one big problem we faced that we still don't know how to solve. That is, you can use that to mutate them to find bugs. But once you find a bug, you need to be able to reduce to something small so you can report. And that reduction process, we don't really have a good solution yet. So we stick with a randomly generated program by a tool called CSME. So that's a simple file program, it's usually a few thousand lines long. And also they have some sort of a tool to guarantee that every program they generate is free of undefined behaviors and is valid. So mostly we rely on those because they're easy to use, simple file, it's easy to reduce. But if we have, I think, good reduction techniques, we can also take this to just using existing open source projects. Since you can argue, bugs find using open source projects are more meaningful, rather than randomly generated by another tool. Yeah, good question.
Did you report on, so you reported bugs to GCC and LVM, but did you find bugs that they created in other open source projects? And like you said initially, when we find this, we often think that we've made a mistake and changed the program.
Okay. Yeah, so let me paraphrase the question maybe. I assume that you meant, have we found any bugs that impacted other projects? Yes, we found a bunch. Sometimes it's very hard for us to know. But there are some cases where, for example, we reported one GCC bug a few days later, and one person was complaining that I'm trying to use GCC to compile media player and player. And somehow if I play this on a particular media file, the media player crashes. And then they were able to trace this back to the bug we reported earlier. Yeah. But this kind of things is a great question, but it's not easy for us to answer. But there's a few cases that we noticed.
Yes. Thank you very much, Jindal. It's very great keynote. So you have given a very interesting and clear view on the equivalence module inputs to test the compilers. So I'm wondering, based on your knowledge, is there the similar approaches has been applied to other languages like Java, Python, or even Android? This kind of things.
That's right. Yeah, a very good question. Yes, we have tried to apply this, although our focus has been on LVM, the GCC, and also the detailed C compiler, and also a bit of Microsoft C compiler. And we have also dabbled into other places, for example, Rust, the Rust compiler, the Go compiler, like the Java, the JVM, all these places. And I think a very interesting domain to apply is the database engines, like Oracle database. Yeah, it would be very cool, SAP databases. The technology, at least the general technology, should be able to apply there as well.
Hi, thank you for your talk. I'm Ray from McGee University. So from one of the slides, I see that there are actually less bugs in GCC than in LVM, but actually LVM is much smaller than GCC. So normally in our expectation, when there are more lines of code, there are more bugs. Can you explain why there are less bugs over there?
Yeah, so that's a very careful observation. And so there are quite a few explanations. One is, for a while, for us, when we report a bug, you like to have very quick feedback from developers. And for a while, the LVM developers were not as responsive as GCC folks. So we focus more on the GCC side. Okay. Of course, it could also be possible because GCC is a larger kind of code base. It contains more bugs. Right? And also, LVM is modern infrastructure. The structure is better compared to GCC. So it's also kind of like likely to have fewer bugs. In the latest few months, we focus our attention more on the LVM. Now we're getting very close. Because there is one or two very active LVM developers who are super responsive to our bug reports.
I'm Shane from McGill University. I have a question about the bugs that you've reported but haven't been fixed yet. Are these just really difficult to diagnose, or are they ones that perhaps were actually bugs? And do you have some insight into that?
Yes, very good question. So the question was about, so I think on the slides I said it was like 1,300 also bugs, close to 800 got fixed, still 500 also got, I guess was not fixed yet. So there are a few categories. One is things that we are actively investigating, still take some time to fix, so there's actually many of such. And also there are some categories of bugs that they don't care as much. So that for us is also a learning process. Which bugs are more important to report, which bugs are less likely to be. For example, for LLVM, we report a bunch of link time optimizing report related bugs. The GCC guys spend the time to fix them. But the LVM somehow they did not pay as much attention. And there's other ones which probably just there's so many reasons less, but these are probably the two main reasons. More questions?
You found several bugs with LLVM and GCC. Any of these bugs were related to the processors also? Because some of the bugs are related to specific kind of processor like coffee date or iDate processor.
Yeah, so excellent. We did not really look at we only test on one architecture. Yeah. It's really just on x86, nothing else. Right? If we tried on other architectures, I'm sure we would find additional bugs. Right? We have been focusing on really just the x86 because that's what we have access to. Right? And also when we focus on from dash 0 to dash 03. O0, O1, O2, OS, O3, that's what we focus. But lately, we also have been looking deeper inside compiler passes. But mostly for x86.